Ladies and gentlemen, Dr. Hod Lipson and the future of 3D printing.
Thank you. Thank you. It's a pleasure to be here. I wanted to talk today a little bit about 3D printing. And this is a technology that's been around for a long time, but only in the last couple of years it sort of took off in a big way and is sort of making waves in lots and lots of different industries. So I used to give talks about 3D printing as sort of an esoteric technology that nobody heard of, and that was enough to get people excited. But today, I have to do more than that. Everybody's already heard about 3D printing, and so what I'm going to do is I'm going to tell you a little bit about where this technology is going in the future. I'll speculate a little bit about what are the next phases of this technology, what is going to happen in the next 10, 20, 30 years in this area of 3D printing. And one message that I'd like you to have, to take home with you is, given that you are learning about this technology and seeing about all its potential, how can we use that in education? I'd say the parallel to this technology today to computers is somewhere around sort of the late 70s, early 80s, when computers were just taking off, getting into schools in lots of different ways, and people didn't know quite how to use it properly for education. So with all your hindsight about how computers could have been used earlier on, this is the same point now with 3D printing, and that's the message that you should think about. So let's talk about 3D printing a little bit. Just to put us on the same page, 3D printing is a technology that fabricates objects by laying material, stacking material layer upon layer, building up a three-dimensional object one layer at a time. So I have here lots of different examples. Too many people to pass this around. I'll leave it here for you to look at later during the break. But I have in my hand here, for example, a 3D printed object. It's all printed in one shot. It's very complicated. It has all these intertwined plastic pyramids, if you like. And this part was printed about 15 years ago. I still carry it around in my bag. It's strong enough, doesn't have any padding or anything like that. And it's pretty high resolution. If you look close at it, you will probably not be able to see this striation with the naked eye. It's pretty solid, and it's printed out of nylon. Also, we've seen a lot of 3D printed tchotchkes out of plastic in the media, and a few people know that this technology can also print with metal parts. So I have here another part that's printed actually in stainless steel. So this part is part of a motor impeller. It's would be very difficult to make using any other technique. It even has these sort of cooling channels at the top that are curved that you can't even make at all using conventional processes. And these curved cooling channels make this particular engine part more efficient than a traditional part. So this is printed in stainless steel. The stainless steel is as solid as stainless steel that you would use on a conventional manufacturing process, such as a mill or a lathe. And this part, I'd say, is about 10 years old. So really the technology has been around, and it's not just about sort of printing small plastic things. It's really expanding in lots of different ways. So let me back up a little bit and say that technology really sort of took off or was born in the early 80s. And here you can see one of the first, the earliest picture I could find of a 3D printed part. You can see photography improved quite a bit since the 80s, but the actual 3D printing technology has been, is pretty accurate back then already. And actually I have a couple more parts from sort of that kind of technology, and it is pretty amazing what that technology could do back in the 80s. What was missing back then is all the 3D design software, the computers, all that needed to catch up before this technology could really take off in a big way. So this technology has been around for a long time, and yet only in the last couple of years it sort of took off in our awareness. Most people, most of my career is in the long period, in the flat line over here, all the way over there. And so nobody knew about technology. It was sort of working in back rooms of companies. But something happened around 2009, 2010 that made this technology sort of take off in a big way. So, and I remember being at a site conference in Hawaii. Glenn Bull and Gerald Kinesic were there, and many others here. We were talking about 3D printing. I guess it was just in the beginning of the curve here. Okay, we kind of realized this is going to be a big thing. How can we take advantage of it, and how can we sort of use it in an interesting way? Since then, a lot of things happened, and technology has gone up. So what has happened that has made this technology, if it has been around for 30 years, what happened in the last couple of years that made it sort of take off? So there's, I think, two important things happened. One is that the price point of this technology went from sort of mainframe to desktop, made it from industrial to consumer. So up until a couple of years ago, technology was always in the tens of thousands of dollars. But in around the mid-2000s, two open source printers came out. One of them was Fab at Home, and the other one was the RepRap from the UK. So these are two open source systems that came out partially in response to the fact that these printers were very expensive. We wanted to have a low-cost printer in the lab that students can experiment with with new materials and so forth, without worrying about voiding warranties and so forth. And so we created these systems, open sourced them. A lot of people started building these. After a while, the MakerBot came out, which borrowed a lot of design elements from these two open source printers, and the rest is history. The MakerBot came out, prices started dropping, and reaching to the sort of below $1,000 for complete assembled systems today. That sort of made the technology accessible to a lot more people. Today, the sales in the consumer desktop 3D printers far exceed the sales of industrial scale printers. And so while it is not, while consumer printers don't account for the majority of the financial market around 3D printing, they do account for a lot of the awareness in this technology, and this is partially why we're sort of learning about this technology today. Second reason that this technology is taking off is the fact that the range of material has expanded. So up until about 10 or 8 years ago, technology was limited to soft plastics that you could make prototypes, but you couldn't make end products out of. You could model things that were later going to be made using some other, more traditional manufacturing process. And as long as the technology was limited to prototyping, all the advantages of being able to make crazy shapes and all that couldn't actually take off because you were always constrained by the end manufacturing process that was going to be used. But a couple of years ago, so the range of material expanded to include lots of what we call engineering materials. This is, for example, printed in, this heel is printed in titanium. And it's something you can buy, and it's very, and it's impossible to make any other way, but you can use this. It works. And by the way, I just want to say all of these slides are available. If you're interested, just email me and I'll send you copies. No need to take photos. So you can print in clay, you can print in wood-like material, and I have a lot of these samples over here again that you can watch and touch later on. You can print in glass. You can even print in concrete. This is a sort of concrete bench. I talked to the person who printed it, and they said they had a time taking it out of the machine. It actually weighs a couple of tons, and they didn't anticipate how heavy it's going to be. But this is a human scale bench. This is a print in paper. So this is a part that's printed by stacking paper, one slice on top of the other and cutting it. This is all done automatically. You sort of peel off the paper you don't need, and you have your paper parts. This is a banana and a grapefruit printed in paper. They are pretty. They look pretty good. They don't taste very good, but they're you know, it's pretty amazing to see that. This is an interesting print in sand. It's a process called solar sintering. You focus sunlight onto sand, and a computer guides the sort of the magnifying glass and gradually melts the sand into an object. And then you can use that and throw it away, and it gradually, after a couple of years, will grind itself back into sand. So it's the most beautiful, energy-free, environmentally friendly technology I can imagine. This is a print in terracotta material. This is printing rice flour. And the rice flour is interesting because it's a material that's available in lots of places, and it is also environmentally friendly. So you can see a lot of directions going. Basically, you can print in any material from cheese to silver. Really, a whole range of materials, a lot of different applications, and so forth. You can also print today in lots of scales. These are large-scale printers that print at sort of human scale, architectural scale, and these are micro-scale printers that print at micron thickness. So a huge range of materials, huge range of scales, and all of that is contributing to the fact that this technology has sort of matured from prototyping to making real things that people use. My personal story with 3D printing actually begins with this robot that we made back in the late 90s. This is a 3D printed robot. Everything white here is 3D printed. But what's also unique about this technology, about this particular robot, is that it was designed by a computer. We took lots of robot parts and joints and bars, and we put them all in a computer, and we let lots of robots compete with each other. The better ones got to reproduce. We duplicated them, created more robots with slight variations, and we threw them back in the simulator. And after thousands of generations, which took about a week on this big computer back in the late 90s, the winning robots got to crawl out into the real world through a 3D printer. And here you can see one of them crawling away. The New York Times had it on the front page saying, "Robots making robots." And the end of the world is near and all that. That didn't happen. It took still a while for this technology to sort of pick up. But since then, in our lab, we've been completely addicted to this technology. We print robots left and right. We print anything we need. It allows us the freedom to create all kinds of shapes and sizes and things that we would normally not be able to do. For example, this is a 3-gram flapping, hovering robot that claps its wings vertically and hovers in place. Everything but the motor and the battery were printed in one shot and allows us to innovate. So again, one of the important things, and we've seen this with computers, and it's difficult to imagine with 3D printing, is that it worms its way into each and every field. There's no field, there's no discipline, there's no industry that is not going to be affected by this technology. The question is not if, but how and when. And this is sort of where we're trying to, this is sort of the message I want you to go home with and think about how it might affect what you're interested in. For example, when this technology began, nobody could imagine it's going to sort of affect fashion and art in such a profound way, but lots and lots of artists and lots of fashion shows are now using 3D printing. Here's another example of a sort of unusual application. This is an area called bioprinting. And you may have heard a lot about 3D printing used to make prosthetic devices and implants. In this case, we're actually printing with live cells. This is a 3D printed meniscus, cartilage of the knee. We took cells from a sheep meniscus, culture the cells, put it in hydrogel, and print a new meniscus and implant that back. The new meniscus is printed based on a CAT scan of the healthy meniscus. So the idea here is that when you're young and healthy, you get a full body MRI scan, you keep it on a USB drive, and when you need a new part, you call it up. And this is where things are going. This meniscus incubates for about 3 months. The cells proliferate, produce extracellular material, and then it's ready to be implanted. Right now it's in animal testing, and I think this kind of technology will be available clinically in about 5 years. So this is meniscus. It's the lowest hanging. It's the lowest, the simplest tissue there is. Lowest hanging fruit, so to speak, in tissue engineering. But people are working on bone Our sort of next thing that we're working on are spinal discs. These are also fairly simple. Everybody needs one, or half the people could use a spare spinal disc, and they're all different. Every person needs a different one and would benefit from it being made out of their own cells. Related, but very different, is this unusual application of 3D printing food. This is something that happened when we open sourced our printers. People didn't print robots and they didn't print bones. They printed chocolate, cookie dough, things like that. And here what you're seeing is a French Culinary Institute in New York printing with celery and scallop, I think. Here they printed a house out of scallop, and here it is fried, just to give it the extra crunch. And you can, of course, print it into a shape of a gear or something else, if that's what you like. Some of you may have read about our 3D printed dinner. Our dinner is printed, I think, was the story in the Sunday Review, New York Times. This is a 3D printed pizza that is topographically correct for Italy. As you can see, it also is on a printed plate and a printed placemat and a printed silverware. So lots of examples there. This is a 3D printed cookie that we made on our printer, and it looks normal, but when you cut it in half, there's text inside. What better way to learn the alphabet? So let me pause a little bit and say a couple of words on use of this technology in education. And this is sort of it turns out that since this technology became accessible to school children, a lot of people have been thinking about how it can actually be used in class. And it turns out that it is a lot more challenging than you can imagine, or more challenging than what I had imagined. And I had naively thought in the beginning, oh, this is a no-brainer. We just have to let kids use this, and good things will happen. I've learned over the past couple of years, also through a couple of NSF grants, that there's a lot more to it than that, as you already know very well. And so this technology sort of made its way initially, and sort of the first wave is into the high school tech shops. And in high school tech shops, it's very easy to see how this technology fits in. They already teach about CNC and machining and all that, so now they have routers. So now they have one more machine for making things, and students that are there are already excited about this stuff, and they use it. So that was sort of the first wave. It's the easy wave. But the question is, what can we do next? And how can we get that in sort of the core curriculum and all the way down to elementary school? So I want to share a couple of examples of things that I've seen, my experience with using it in teaching, and maybe that will seed some ideas, because I think this is still an open question of where this might go. So for example, one thing that we did, we have this at Cornell, this collection of kinematic machines from the 1860s, which when Cornell was founded, the founders bought all these kinematic systems for teaching mechanics to engineers at the time. For a long time, those machines, it's a unique collection. They were online, there were videos, there were pictures, there was text, but you had to actually come up to Ithaca to see and touch those machines, to use them. Well, today, we have all of them online in a format that you can download and print your own copy. And so you can download the copy of the machine, print it your own, and it works. And it's something that now people around the planet download these copies and use these machines to teach kinematics around the world. So these machines, which were once confined to this museum, are now used everywhere, and it is sort of, they got a new life through this process of engineering. And this is done at lots of different scales. This is a teacher in Brooklyn, Ryan, who's using this particular 3D printing technology based on a MakerBot curriculum to allow children to print copies of their houses, the buildings they live in, and watch how water erosion shifts the foundation of the houses and what happens there. So This sort of is another example of sort of how you can use this technology to get kids engaged in understanding things, and it brings sort of their personal element to it, because every child actually can see what would happen to their own building, and so it makes it's not as abstract. This is a great example of using it with visually impaired students. This is when I started working with 3D printing. I got this email from someone who said, "I'm a blind, I'm visually impaired, I can't see, but I remember when I was a student and we learned thermodynamics." This is an undergraduate student. Because I couldn't see the 3D diagrams that the professor was drawing, the professor went out of his way to create this clay model that I could actually put my hands on and feel how things vary in X, Y, and Z. That was, he said in the email, was very important, and it really was a breakthrough, and it allowed me to understand the spatial relationships that we were studying. That professor retired, and that clay model stood somewhere on a shelf, never to be used by anybody but that single student. So this man wrote to me and said, "How about we scan this object so that other visually impaired people, students, can use it around the world?" And so we did that. The professor sent me the clay model. Here it is on the left, the original one. It arrived shattered, so we had to reassemble it carefully. We rescanned it, and on the right you see a 3D printed replica. It's printed in color. It's pretty. It looks and feels like the original, and it's posted online. And again, other people who might want to use this for teaching can do this. So this is an example. I don't know if it actually is being used anywhere, but it changes our way of how we can address, for example, in this case, visual impairment by sharing teaching models that would otherwise sort of die a slow death on some dusty shelf somewhere. Now they can get a new life and find new uses. And I think once this technology becomes very popular, there's also going to be more incentive for people to create these models, because they wouldn't be just creating it for their own students, it would be creating it for the world. But to me, the most exciting way of using this technology is not by creating teaching models. It is by allowing students to design their own products. This is, I created a 3D printing summer camp about a year and a half ago. And students, this is at Cornell, students arrived for a week in the summer to do 3D printing. And I have to say, most of the students arrived there, they didn't want to be there, they were sent by their parents, kind of rolled their eyes and sat down. And we thought, okay, what are we going to do to make this interesting? And usually we do tours in the labs and they see what it's like to be a scientist and all that. But instead, we said, okay, we're going to teach you how to design your own product and sell it. You can make a profit by the end of the week. And see, these students sat down and started designing things. They knew nothing about design. Within about 2 days, they were up and running with the software. Within 2 more days, they were already refining. And in the 5th day, they already uploaded their designs to a website where they were selling it. This particular kid designed this interesting pencil holder that you see there. It was selling it out of bronze, printed in bronze online for a profit by the end of the week. And it's interesting, on one hand he was holding his jailbroken iPhone with God knows what on it. And on the other hand, it was raised, and he was asking, what if somebody steals my design? And you couldn't have a better sort of introduction to intellectual property than that. So I thought that was very interesting. Now I teach product design at Cornell for sophomores, second-year students, and they, for a long time we used to teach them, mechanics and theory and all kinds of things. But today, what we do is we say, take the semester and design something and sell it. And we go through the entire process, and I actually told my students, if somebody that does not know you personally will buy your design at cost or more, you get an A+. That's sort of the bottom line of your design. If you design something somebody else is willing to spend money on, you made it. I don't know how I'm going to enforce it because everybody has a second cousin that's going to buy it for, stuff like that. But I think that's sort of the empowerment of not designing it for your professor or for your teacher or doing something like that, but actually being there on the real market, seeing what your real worth is very, very exciting and empowering. The kids design all kinds of things. This is an iPhone holder. This is a beautiful teacup that is unique in that it's printed in ceramic. And it's unique in that what the students did, they designed a place for the tea bag to go so that when you when you pull the string, the tea bag squeezes and stays tucked in the cup, so you don't have to sort of move it around, and drip everywhere. And that an investor contacted this team to mass produce this teacup. In the Sunday Review Dinner's printed thing, the teacup, I don't few people know this, but here's the teacup actually being used for something. So it's a real thing. This is another example. Another team designed these kind of slat glasses for, and it has this Cornell University. It's cool. It's nice. It works. They designed this, and they had 50 people buy their glasses. It was a very exciting moment. But then they realized they will not be able to deliver 50 units by the last day of the semester, which was when all the celebrations happened and where the time their customers wanted these glasses. So the last day of the semester is like a cliff, okay? One day later is useless. You have to deliver by that day. They were not able to deliver it, and they lost all their customers. I couldn't have created a better learning moment than that. You can have deadlines on submission and whatnot, but when these students actually experience a real deadline, a real issue, and this sort of learning opportunity is priceless. So these are all kinds of things that I think really are exciting that are happening with 3D printing in education. It's not necessarily just printing teaching models, although that's a very good thing, a lot of opportunities there, but it's this empowerment. I can tell you from my experience that also nothing gets kids more excited in elementary school when I showed this to my son's class than printing cookies in the class. Kids who couldn't care less about math, who couldn't care less about programming or design, couldn't care less about robots and all that stuff, suddenly get excited. And they say, what if we change it a little bit so it's a different design? What if we print more? How many cookies can we print from one batch of material? How much should we sell them for in order to make a profit? All kinds of different angles, and people get engaged that in ways that you couldn't imagine before. I've also seen this happen with design software. This is Minecraft. You probably heard about this sort of virtual Lego tool that a lot of kids are playing with this. I didn't realize how pervasive this is. My son doesn't stop talking about Minecraft, and I was at the parent-teacher conference just last week, and I asked the teacher about it, and she said he's actually not the kid that talks about it the most. They all talk about it, including both girls and boys, which is a very interesting development because most of these video games hit only boys. And so they design and make things and print them. They design things very quickly. My son just the other day needed a house for something, and I saw him within 60 seconds make this thing, and then clicked on Shapeways, swiped my credit card, and within a week, he was holding this in his hand. And it's just amazing that you can do this so quickly. He's now setting up a shop to sell menorahs for next year. And to me, this is really the new lemonade stand. Okay, this is you don't see lemonade stands anymore, but this is the new lemonade stand. It's the same trend, just like the students are selling things online. Now kids can make things and post them and have a website and can start making things and selling in a different way. And to me, it's an incredible empowerment that I think is priceless. So let me sort of point to a couple of different aspects of the technology that are going to be disruptive. You know, when we wrote our book on 3D printing, we interviewed dozens of people, and everybody told us how they're using it and so forth. But we found that instead of sort of going through lists and lists of different applications, all of these different people kept repeating the same reasons of why they started using this technology. It ended up we always heard the same sort of 10 reasons come up in different ways. So I thought I'll just list those. I'll call it the 10 disruptions of why this technology is disruptive. And if you can see how this technology, how one of these sort of principles affects what you're interested in, this is something that you should pay attention to. So the number one disruptive principle of this technology is that manufacturing complexity is free. What does that mean? It means that making something complex takes the same amount of time, energy, skill, effort as making a paperweight of the same mass. This is a market departure from most of human history, where making complex things usually took more time, effort, or skill. This opens up a lot of opportunities. For example, in the aerospace industry, parts are being made now. This is from Airbus. You see in the background the original part, and you can see in the foreground a part that's more complex but is lighter. It would be expensive to make this kind of part before, but because complexity is free, it's not more complex to print the part in the foreground, and it can be used, and it is lighter, saves a lot of energy and fuel over the lifetime. Second reason this technology is disrupting things is because variety is free. The same machine can make a lot of different things. Now, most manufacturing processes can make a variety of things, but the variety isn't as large. Most systems, processes, traditional manufacturing processes, if you want to make something else, you have to change the machine, you have to set it up differently, and so forth. All these parts printed on the same machine, same print job. That allows, again, for lots of new things. This is, I think, the best business example of using this idea. These are Invisalign braces. They're orthodontic aligners. They're printed in plastic. And there are 50,000 of these printed every day. I didn't know, I triple-checked that number. It's not 50,000 a year, it's 50,000 a day. There's probably somebody in this room who's wearing these. I won't ask for a show of hands, but these are all, each one of them is different. Each one of them is complex, and making these wouldn't be viable using conventional manufacturing processes. But because complexity is free, because variety is free, you can make these things and it becomes economically viable. Third disruptive element is that no assembly is required, and that chain, for example, which I have here, is all printed in one shot, all the parts pre-assembled, and you just take it out of the machine like that. There's gel printed between the pieces. You wash the gel out, and you have your chain. The fact that no assembly is required is very disruptive to many industries because most of the labor cost is in assembly. Most of the errors are in assembly. Most of the problems with things coming apart are because of assembly. There's fasteners in supply chain because of assembly. That's a lot of overhead. And in fact, when you can make parts that don't need assembly, you can make them more efficient. This is a air duct in the aircraft. Because it used to be made of multiple parts, because it's made of one part, it can also be smoother, lighter, the air can flow more fluently through it, and so forth. There's also much less lead time from the point you have a design to the point you start production. In most manufacturing processes, that is a long period from end of design to beginning production. Here, it's almost immediate. This means you can iterate very quickly on design. This is where a lot of companies are using this technology. I came to the lab one day to find a bucket, the trash can full of iterations of some design. Here they are. I pulled them out of the bucket. And on one hand, I was mad of all the garbage that was produced. And I was worried that we're switching into a sort of computer science mentality of development where you debug things. So you make the hole a little bigger, it's too big, print a new one, too small, print a third one, and so forth, and we iterate by debugging instead of think twice, cut once, which used to be the mantra of engineering. With printers, that's not true anymore, but you can innovate very quickly, and never before was a student able in one day to design something as complete and go through so many design iterations as this. So you can see there's a double-edged sword. There are also zero constraints on this, the geometry. This is a big thing. You can make things that are very, very complex, things you cannot make any other way. And this is different than complexity is free, which means that complexity doesn't add more money. This means that you can make something that it was not even possible, free or not, before. This is a 3D printed bench out of marble, and this is a nose implant printed in titanium. I have that here also. It's new, it's not used, so you can feel free to try it out. But it's has a complexity that's just impossible to make any other way, and so forth. There's almost zero skill required to use this machine, which means kids can use it in the classroom. I mean, if somebody would have told you a couple years ago that kids could manufacture plastic objects of arbitrary complexity in the classroom, that would have seemed impossible. But it is, and it has to do with the fact that all the skill is in the software. The design is where the skill is. The actual manufacturing is almost skillless. This is good and bad. I was visiting a manufacturer that was making aerospace parts out of steel with printing, and I asked them, what kind of education do your employees have to use this machine? I was hoping he was going to say, well, we rely on you for your PhDs, the students and all that. But what he said is, as long as they can show up on time, clean and sober, they can operate the machine. And that's never before could you make these sort of very complex aerospace parts with so little skill. So again, this is you can already see that this has pros and cons in different ways, but it definitely puts all the onus on the designer rather than the manufacturer. It also means that a lot of people can make things they're not supposed to. To me, so I've been speaking about guns a lot, not because I'm interested in guns, but because of 3D printing. And my point of view has been on these 3D printed guns that I'm not worried that criminals and terrorists will print guns because those people have other ways to get guns. It's that kids will print guns. This is really what I'm worried about. And that these kids might inadvertently injure themselves in trying to use those guns, because these are not good guns. They are more likely to blow up in your hand than to actually shoot, and that's why it's dangerous. So this sort of opens up this whole area of safety, and as long as people and kids are printing plastic tchotchkes, it's okay. But the moment they start printing bicycle pedals and helmets, we have an issue about safety, reliability, liability, quality, all these different things that right now are unsupervised and unregulated. There's also compact, this technology is compact and portable, which means it can be moved around to new places. This is in comparison to a traditional injection molding machine, which is more difficult to move around and carry. This means this has implications to supply chains and how we can make things where we need them, distribution networks and so forth, instead of sort of centralizing things, and that is a big disruption. There's less waste produced by this technology when printing in metal. There is more waste when printing in plastic than injection molding, but in metal there's less waste. This is a large-scale turbine printed in titanium in China, and it's something that would generate a huge amount of waste material if you did it the usual way. There's less, they can create new materials by combining existing materials, and you can create new things by combining materials in new ways. And this here is an example of a printed heart valve out of live cells that combines both hard and soft cells. And because you combine hard and soft cells, you can a heart valve is actually requires this transition between different cell types, and that's something that would be very difficult to make even using other advanced tissue engineering methods. This is very important because when you implant traditional heart valves in children, as the child grows, the heart valve needs to be replaced every year or so. But if you print a heart valve out of the child's own cells, this heart valve grows with them. It's a different experience. At least that's what we hope. I'll conclude with the last disruptive principle, and that is the idea that you can replicate things, that things can be duplicated and copied, very much like music and so forth has been copied. This again is very interesting, has lots of positive implications, and also has a lot of people worried about intellectual property and so forth. Will there be a Napster moment in this area or not? For educational perspective, here's an example of, on the left is a 3,000-year-old cuneiform printed in clay. The original was made in clay. On the right, you see a replica of that cuneiform, which we scanned the original and printed the copy. I have the copy here, or maybe it's the original. We don't know. It's feels and it is the same color. It feels the same. It weighs the same, and you can see how what this means, that when you scan objects in the field, you can fax them over somewhere else, and scholars can start studying them right away. So these are many of these sort of teaching and scholarly articles are not. It wouldn't be economically viable for any mass manufacturer to actually produce these as teaching models or for scholarly use. But with this, you can do it fairly easily. So this is sort of where the technology is today. Market trends are very sort of interesting. There's if this is all of manufacturing around the world, about $2.5 trillion. This is U.S. manufacturing. This is 3D printing. It's very small. The only reason you can see it is because I have a thick outline around that dot, but it's actually pretty small. It's about $2.5 billion. Very small industry, making a lot of waves right now, but it's not going to make a big dent in mass production, but it is growing very fast. It's growing about 25% per year in the last 3 years. People are using it in lots of different ways. This is a recent survey. If you look at sort of the breakdown, you'll see half of people still using this technology to prototype things that they later will make using some other way. But a growing portion are actually using this technology to make real parts. And this is direct part production is growing now to about 20% of use of this technology is in making parts that are not prototypes, but actually end parts that are being used for real production. And this means that the technology is, because it's an end part, it means that it actually, we can take advantage of all these disruptive elements and really take advantage of this complexity and all these things that we can't use using conventional processes. Around the world, it's very interesting to see how this technology is catching up. When we published our book in English about a couple of months ago, within 1 weekend, the book was translated into Chinese. There were 15 chapters, 15 translators, and it was translated and showed up in Chinese the next week. It was, and it sells a lot better in China than in the U.S. per capita. Now, it could be that the translation is better than original, but maybe it's also because in China, people are more interested in manufacturing, and it's very interesting to see sort of the reaction of people wondering how this is going to affect their job, what can they do, and so forth. Chinese government has put in $240 million into academic research in 3D printing, compared to about 30 million in the U.S. There's 100 hacker spaces that were created overnight in China, where people off the street can come and start playing with this technology and innovate. So the world is sort of catching up, and while it again feels like the U.S. is leading this, Europe is leading, so the metal printing is China is catching up very rapidly. And this is a global sort of innovation accelerator that people are using in different ways. And it's important to understand this, the ecosystem really comprises printers, materials themselves, design software around all of this, service providers that can actually produce things for you, so you don't have to own your own printer if you're printing in metal and so forth, and designers, new designers that are emerging and using this technology in in different ways. So I think there's a lot of opportunities happening, lots of different things, lots of opportunities to grow, and sort of we'll see where this thing ends up. So I want to end with this big question that everybody's asking, is where is this technology going next? And I have to disclaim first that I don't know where it's going next for sure. And it's a little bit like trying to predict where computers would go next in the 70s. Right? So everybody at that time knew and could predict that computers are going to revolutionize accounting. And the computers will revolutionize military calculation. Everybody could predict that, and that happened. But nobody could predict social networking and the other things that happen. So we're at the same place today where we can easily predict that these printers are going to become faster, cheaper, and better. And you could be listening to nothing in this talk, and you know at the end that computers are going to be cheaper tomorrow, they're going to be higher resolution, better material, smoother surface finish, all these different things are going to improve. That's a no-brainer. And certain things they're going to affect prototyping and all that. But what's going to happen after that? We know printers are going to start having feedback, so they can actually watch what they're printing and improve and learn as they print and all these kinds of things. But what's going to happen in the long term? So my view on this is that sort of this technology is moving in phases, and today we are at the end of only the first phase. So let me tell you what these three phases are, and I can sort of get you to think about where this technology is going. So today we are at the end of the first episode where we have complete freedom to print any shape that we can describe to a computer. Any shape you can imagine that you can describe to a computer, you can make. Okay, that's an incredible freedom that we never had, and it allows us to make things that we can't make, again, any other way. The problem with this freedom is that it is very difficult to describe shapes to a computer. And in fact, the design software is sort of the bottleneck right now. Machines can make very complicated things, but design software isn't there yet. It doesn't allow us to design, and that is where we're stuck today. So I think in the future, closing these gaps in design software will become much more sophisticated. Here's how I imagine things, that you will have your printer at home and you walk up and you say, printer, I need a bracket for my shelf. And instead of buying a bracket from the web from some fixed collection, fixed variety, you say, here's my wall, it needs to carry a load in this direction, and you say, design it for me. And the computer will design it for you based on whatever materials you happen to have in your printer, and it'll come up with this particular design. This is running in real time, based on mechanical properties, and it's designing automatically a bracket to hold something up. I might say, actually, you know what, I changed my mind. I just realized I want this area to be open because I need to pass a pipe. You hit enter again, and the computer redesigns it to accommodate your request. So we begin to think about design just like we let the printer make things, we'll let the printer also design it for us. And this technology will improve. There's lots and lots of ways to make it work. You can include multiple materials and make things more exciting. So this is where I see sort of the first episode. Complexity of geometry is free, but design software is catching up, and that's where what things will look like the next couple of years. Second episode is when we involve multiple materials in a single print, and we use the printer to make new kinds of materials. So the first thing is using a printer with multiple materials. This is a little bit like transition from black and white TV to color TV. Most printers today print with a single material. They print just one material, but you can feed in multiple materials into a printer and print things with multiple parts. Here's, for example, I have a couple of things that have multiple parts printed in different ways. This is a robotic gripper that has hard and soft material in it, and it works. It's printed in one shot, no assembly, and it has sort of the soft gripper at the tips and so on, all printed in one shot. So this is sort of multi-material. But you can also create new materials on a printer. And just like with just black ink, you can create lots of shades of gray. Even with one material, you can create lots of new materials. For example, here you have a kind of mesh that's soft, made out of hard plastic that's printed in a particular structure. This is metal foam that is lighter and stronger, has a better weight to strength ratio than traditional materials. This is a sort of fur printed out of nylon, and this is a cloth that I have here, a sample. That's very sort of fine chainmail that's printed that's printed in sort of acrylic. And I actually have a tie made out of this, but I forgot to bring it. So these are all sort of opportunities to make new kinds of materials from one material, but just printing it in different ways. And this is sort of a new space which we're just beginning to explore, and I think will be the future. This is sort of a foam material that one student discovered by accident when they were trying to print the thing on the left, but they accidentally left the nozzle too high. And just like when you pour honey, it meanders and creates this crazy sort of stochastic pattern. Instead of getting this, they got this on the right. It turned out that they didn't throw it away. They thought, hey, this is a foam. This is an interesting thing. And this is now of a lot of interest to sort of non-woven fabric industries. You can sort of print foamy materials in lots of different ways. This is a sort of two-dimensional zipper, a material that can come apart and be reassembled in different ways. The last episode is moving from integrated, from printing passive parts, like all the things I'm showing you here, to printing integrated systems. So from printing sort of parts that are just sit there to printing sensors and actuators and wires and electronics. So going back to my story with the robot that I printed, I was very frustrated at the time that I could only print the body of the robot, but I had to manually put in the wires and the batteries and everything else. So we set out to print everything else. And I have here an example of a printed, printed wires inside a robotic finger. This is a printed battery that you can print into any shape. This is a printed actuator that bends when you pass current through it. And to test this out, we thought that we want to print a telecommunication device. Everybody talks about, will you one day be able to print your cell phone? So that's very difficult, but we said, let's try to print a telegraph machine. First step first. Turns out the first telegraph machine, one of the first two, the original ones, was at Cornell. We found it in the dean's closet somewhere. We dusted it off, made a copy of it in the foreground, and then we printed the whole thing, including the wires and the magnets, and we sent a message and received a message with it. If your Morse code is not up to snuff, this is what the message said. So it actually worked, and it is 100% printed. Here's another example of a recent work that we've done printing a loudspeaker. It's 100% printed, including the magnet and the coil and everything else. I have the benefit of increasing the volume here. So this is the loudspeaker actually being used.
New workers are mastering the 3D printing that has the potential to revolutionize the way we make almost everything.
So if you recognize that voice, it means the speaker works. And you have to believe me that it's coming out of the speaker there. That's 100% 3D printing. So I think it is the first 100% 3D printed consumer electronic device. It's very simple, but it sort of shows you where things are going. And we're now working on embedding circuits inside the 3D printer as it's printing. And I think, as this technology matures, we'll start printing these complex things. Our goal is to have to print a complete robot that will walk out of the printer, batteries included. It's still, we have ways to go. This is our first robot. It's a fish. It has battery and it flips its tail, but unfortunately it didn't work. But it does float. So that's at least one step towards a real fish. So let me end with this big question that everybody's asking. Is this a hype, or is this sort of the peak, or is this going to go forward? And some people believe that, that it is not living up to its promise. My claim is that we haven't seen anything yet. This is just the beginning. And the reason is that if you look back, you'll see a common thread through all industrial revolutions. And that is that something that used to be expensive went almost to zero, changing, and that had a cascade effect on many industries. The first industrial revolution, the cost of power went to zero. Before steam engines, power was expensive, coming from animals and water wheels, but after steam engines, power was relatively free. It's not completely free, but it's relatively free. Every watt became much cheaper, creating a cascade of innovation in railroads and whatnot. Second industrial revolution, when the cost of computation went almost to zero. Before the electronic computer, the best calculator could add a couple of hundred numbers an hour. Now we can add billion numbers a second. Third industrial revolution happened when the cost of communication went to zero. In the Pony Express, you could send a letter and may or may not arrive a couple of weeks later. With electronic communication, you can send terabytes around the planet and not think twice about whether or not they will arrive. The fourth industrial revolution happens when the cost of making complex things goes to zero. With 3D printing, it doesn't matter how complex your part is, it's the same cost, time, effort, skill to make it as it is to make a paperweight, and I think that will change things forever. So if we think about what differentiates us humans from our evolutionary ancestors, we often talk about tools, and I think this is perhaps the ultimate tool. Thank you.